All right, this will be our first video for Monday, June 29th, and we're going to begin by looking into Chapter 10, and we're going to begin talking about liquids and solids in Chapter 10. So we're going to go into a little bit more detail about their actual chemistry than you've probably seen before. So let's go ahead and get started. The first place we like to start with when we're talking about especially liquids, is something called intermolecular forces. All right, so I'm going to spell that out. So intermolecular forces. So when you see the prefix inter, that means between. All right, so this is going to be forces that are between molecules. All right, so believe it or not, the word molecular relates to molecules, but let's kind of try to define what a molecule actually is. All right, so a molecule, a good definition for this is it's a discrete compound between, between is probably not a good word here. Let's say with two or more atoms bonded via covalent bonds. All right, so let's take a look at a classic molecule, and that is water. All right, so I'm drawing the Lewis structure of water here. All right, it is a discrete compound. And what I mean by discrete compound is it is made up of H, O, and H, and that is it. All right, so one molecule of water has these three atoms, and the atoms are linked via covalent bonding. All right, so water is a molecule. All right, however, if we look at something like sodium chloride is not a molecular compound, so thus we don't consider it to be a molecule. All right, it is what we call an ionic compound. All right, and the sodium and chlorine atoms, all right, are actually held together through electrostatic forces, or that's basically a fancy word for the Na pluses, or coordinated to the Cl minuses, and that's the electrostatic force that's holding them together. But it's a lattice-like structure, all right? And what I mean by that is it's not discrete. So we'll get into this later when we talk about solid structures. But what we see here is a ionic bond between a sodium and a chlorine ion, all right? And then they make this lattice, all right? So we see things like this, where each one of these intersections or ends of lines can be something like a sodium atom or a chlorine atom, all right, that are held together by the electrostatic interactions, all right? So you think of something like a salt crystal, all right? It is, an infinite, finite, but tons and tons and tons, or billions and billions and billions of Na and Cl's that are repeating over and over again, all right? And they are all locked in together, whereas water is, if you look at a glass of water, it's, billions and billions and billions of HOH molecules, all right, but they are not in a lattice-like structure in liquid water, all right? So you can have one single water molecule floating around in a solution, whereas sodium chloride in its solid form is a lattice, all right? So it is not discrete. It's not a singular compound. Is what I mean by that. All right. So what we're going to look at now are what are these intermolecular forces, and again, we're only going to be considering molecular compounds. All right. So what we're going to be looking at is something called van der Waals forces. All right, and this was named after a Dutch chemist. All right, and he had looked at these, what we call three forces that hold molecules together. All right, so when we talk about them being held together, all right, so let's look at two particles here, and we're going to just pretend these particles happen to be molecules of something. It could be water, it could be sucrose, it doesn't really matter, all right? They are attracted to each other somehow, all right? And that attraction is what we call the van der Waals forces, all right? So depending on what those particles are, they're going to have different types of intermolecular forces, all right? And that's what we're going to go through now. So the first thing that we're going to look at is what's called the London dispersion force. And sometimes this is just truncated down to the dispersion force, all right? But, you know, the London word kind of persists, or sometimes people just call them London forces, all right? So London dispersion or London or dispersion, right? Forces is something that is intrinsic to all molecules. So what I mean by this is an attractive force between any two molecules. So the requirement, if you will, to be able to participate, if you will, the dispersion force is that you just have to be a molecular compound, all right? So these London dispersion forces, these arise from something we call temporary dipoles. All right, so let's just kind of review what a dipole is. So a dipole is just where you have an imbalance in electron density. For a molecule. All right, so we look at a very simple molecule like hydrogen bromide, for example. All right, I'm going to draw its Lewis structure. All right, so recapping from your periodic trends in Chemistry 111, we have this concept of electronegativity, and that's the propensity of an atom to draw electrons in towards itself. All right, so the bromine atom is more electronegative than the hydrogen atom. All right, so what we do is we draw these little symbols, a delta, which means partial, and it's negative. All right, so it's a partial negative charge over there for the bromine because it is more electronegative. And since the hydrogen is losing electron density to the bromine atom, we have what we call a delta plus over there, or partial positive. All right, this is a lot different than something like sodium chloride, all right, an ionic compound where we have ionic bonding, which is much different, obviously, but we have a formal positive charge on the sodium atom and a formal negative charge on the chlorine atom. There's no partial there because in ionic bonding, there's no sharing. All right, so that's not what we're talking about here. We're talking about molecular compounds where there's a sharing of electrons, all right, but most of the electrons are going to be hanging out towards the bromine atom, and this is what we call our dipole. All right, so we have something called a dipole moment, just kind of reviewing here. We draw with that symbol there. That's just showing us that the electron density is heading towards the bromine atom. All right, now this is actually a permanent dipole here. All right, the hydrogen doesn't ever take over and, you know, pull the electrons towards itself. So we're not talking about a temporary dipole in the molecule hydrogen bromide. That has a permanent dipole. So what is a temporary dipole? Well, why don't we go from hydrogen bromide to the molecule bromine? All right, so this is molecular bromine, or Br2. All right, so there's its Lewis structure. Now, bromine and bromine have identical electronegativity values, so you're not going to put a delta minus or a delta plus on either one of these atoms because they're the same. However, bromine could come into contact with another bromine molecule. All right, so molecular bromine exists as a liquid at room temperature. So these could be, you know, two bromine molecules floating by each other in liquid phase. All right, so what's going to happen is, right, this molecule is going to bump into the neighboring molecule. All right, so when they bump into each other, they're going to cause the electrons to kind of blob out into another direction. All right, so you want to think about this kind of like a lava lamp. All right, two of those lava bubbles kind of bump into each other. All right, and then they kind of just kind of blob into a different shape. All right, so when that blobbing happens, that kind of throws the electrons around. All right, so the electrons could go to one end or the other, and we can imagine something like this happening, where let's say all of a sudden the electrons start just hanging out over here. So we'll put a delta minus over there, right? And then if they start hanging out over there, well, then you're going to get a delta plus over here, all right? And then let's say on another blob that got bumped into, you get a delta minus over there and a delta plus over there, all right? So all of a sudden, you've got a delta plus near a delta minus, and that's going to result in an attractive force, all right? So you don't actually, need to think about these blobs so much, but you just need to understand that all these molecules in a container are bumping into each other at all times, no matter what phase they're in, whether it's gas, liquid, or even solid, all right? But they are bumping into each other, all right? And that's causing these temporary dipoles, and that is a result, and as a result of that, we get an attractive force there, all right? So this is called the London dispersion force. And of the three van der Waals forces that we're going to cover, this is actually the weakest, all right? The next two are much, much stronger. However, don't discount that the London dispersion force is insignificant. It's very significant, all right? And the dispersion force scales on two things. It's going to be what we call size and surface area. All right? So as a molecule becomes larger, all right, it can have larger dispersion forces, all right? And the larger the dispersion force, the more attracted they'll be to each other, all right? And we'll get into surface area here in a moment. So the easiest way to really evaluate, how strong intermolecular forces are, I like to look at something called boiling point, all right? So why do I like to look at boiling point? Well, if you consider what happens when something boils, all right? So let's just go back to water for a second, all right? So when water is in its liquid phase, so I'll put a little cursive L there, all right? What do we imagine the molecules of water looking like? Okay, they're kind of close to each other, sliding by each other, something like that, all right? Whereas when I heat this, I still have water, of course, but now I'm going to go to the vapor phase, right, or the gas phase. And now those same molecules are spread out much, much further, all right? So heat, of course, is a form of energy. So the tighter the liquid particles are held together, the more heat or energy is going to be required to break them apart, right, pull them apart, and let them go into the gas phase, all right? So boiling point is a good way to look at how, or I guess you could kind of say, correlate how well things are stuck together or how strong their intermolecular forces are, all right? So what I'm going to do is take a look at three halogens, all right? There's the molecular chlorine, right? These guys are all in group 17, all right? So this is Cl2, or chlorine gas. Oop, kind of gave away where I'm going. Then there's molecular bromine, or Br2. And then there's iodine, all right, or I2. All right, so I don't have a periodic table handy, but if we look at group 17, all right, we have F, Cl, Br, and I, all right, as we're going down. Okay, over here would be, in group 18 would be neon, and over to the left would be group 16, which would be oxygen. All right, so we're just looking down this particular column, And as we go down a column, our periodic trends tell us what's happening as we go down here as far as size is concerned, all right? So what we're saying as we go from fluorine down to iodine, size is increasing. I guess I spelled that right. All right, so size is increasing as we go down the column, all right? So if we go back and look at our chlorine molecule versus our bromine molecule versus our iodine molecule, we're going to say that iodine is obviously going to be the largest, and chlorine is going to be the smallest. All right, so at room temperature, all right, so at 25 degrees C, which is roughly room temperature, chlorine exists as a gas. All right, bromine at 25 degrees C is a liquid, and iodine at 25 degrees C is a solid. So what does that tell you about their intermolecular forces? All right, so chlorine, the smallest of the three halogens that we're looking at here, all right, is a gas at room temperature. That tells me that at room temperature you have enough heat to separate the molecules all the way out into the gas phase. All right. Bromine at room temperature, you do not have enough energy to separate them out into the gas phase, right? Because they are more strongly attracted to each other. That's because bromine's larger. And iodine is so large that you don't even have enough energy to separate the solid out into the liquid phase. Now, a little caveat here: iodine actually is a material that sublimes at room temperature and standard pressure. All right, but you get the point. We go from a gas, a liquid, to a solid, and that's because we have this intrinsic energy at 25 degrees C. And if we look at chlorine, it's so small that the 25 degrees C is enough heat energy, or there's enough heat energy present, to separate the particles into the gas phase. All right. So what could we say is trending here is that we get larger, all right, in this group, that we're going to expect what in their boiling points. All right. I would say that chlorine is going to have the lowest boiling point. Bromine would have the second lowest boiling point, second highest boiling point. And then iodine is going to have the highest boiling point. All right. So size will affect the dispersion forces. All right. Now I want to get into surface area next. So I'm an organic chemist, so I'm going to, dabble a little bit in something called a line angle formula. All right. So that is actually a molecule. All right. So some of you may have seen this before, but for those of you that have not, all right, this is the molecule pentane. All right. So like the Pentagon up in Northern Virginia, that is a 5-sided structure. All right. And pentane is a organic compound that contains 5 carbons. So line angle formulas in organic chemistry, we so often deal with what we call hydrocarbons, or compounds that contain both carbon and hydrogen, that we have to do shorthand notation for them. And with line angle formulas, every terminus and intersection of a line counts as a carbon atom. So this is a terminus here, so that's a carbon atom. All right. This is an intersection, so it's a carbon atom. Intersection, that's a carbon atom. Intersection, carbon. And terminus, carbon. So right now our carbon count is 5. All right. So that molecule is C5. All right. Or contains 5 carbons. Now, where the heck are the hydrogens, right? Well, the hydrogens, they're on there, but we shorthand notation by assuming that carbon makes 4 bonds, all right? And if we don't draw anything on the carbons, that they are assumed to have hydrogens on them, all right? So if we look at this carbon right here, it has how many explicitly shown bonds, all right? And the answer to that is 1, all right? It is explicitly shown to be bonded to this carbon there, all right? So we're missing how many other bonds to carbon, and the answer is 3. So I'm going to draw those in and there's where the 3 hydrogens are. All right, so there's 3 hydrogens there. What about now this carbon here that I'm kind of daubing pretty heavily? All right, how many explicit bonds are shown there? And the answer is 2. All right, 1 to the carbon we were just working with, and 1 to the carbon to the left of it. So there should be 2 hydrogens implied there. And you see the pattern. There's 2 hydrogens there, 2 there, and finally we repeat the 3 over here. Sorry. All right, so we count the total number of hydrogens. We got 3 plus 2 gives me 5, another 2 is 7, another 2 is 9, and another 3 gives me 12. All right, so it's C5H12. That's the molecule pentane. All right, so what I'm going to do is redraw pentane below here, and I'm going to draw a isomer of this compound called isopentane. So down here we have pentane and isopentane. So an isomer is a compound with the same chemical formula, but it is a different molecule. All right, so clearly they look different. All right, this is what we call on the left here, the pentane. That is a straight chain. All right, there's no branching. And in isopentane, we have something called branching. All right, because what we have there is 1, 2, 3, 4 carbons in a row, and then we have a branch up to that 5th carbon. All right. So my question now is, for these isomers, which one's going to have the higher boiling point? All right. All right, and how the heck could you tell? All right, well, obviously you could Google it, but you could you'd have to know pentane and isopentane are their names, by the way. But we can do better. All right, we can infer what we've learned about with dispersion. All right, so it comes down to what we call surface area. All right, which ones can stack better? All right, so why is stacking important? All right, well, stacking, when they stack very nicely, that's going to give us the most overlap between the atoms, and that way we're going to get the best dispersion or the best attraction between each other. All right, so what I'm going to do in blue is draw a neighboring pentane molecule. All right, so look how well we can get those to fit, and guess what can happen? Attractive force between all these carbons. All right, very nice. We can get all 5 carbons to kind of overlap with each other and stick together very nicely. All right, now let's try isopentane. All right, so I can get 4 there, right? But remember, I've got to deal with this group here, okay? So what am I doing here? I got 1, 2, 3, 4 that I was able to overlap, all right? And that's not as good as getting 5 to overlap, all right? So is that going to make a difference in their what we call London dispersion force, where they're attracted to each other? And the answer is yes, all right? The boiling point for pentane is 309 Kelvin, all right? And the boiling point for isopentane, all right, is 283 Kelvin. All right. So is that a big difference? Yeah. I mean, that's, 17 and 9 gives me 26 degrees. All right. So that's the difference between freezing and room temperature in Celsius, right? So, yeah, that's not good. All right. As far as being able to say one's got good dispersion forces and the other one's got poor dispersion forces relative to each other. All right. So to recap, we've talked about a compound having dispersion forces driven by size. All right, and then we have dispersion forces driven by overlap or surface area. All right. Okay, so the next force I want to move on to is the dipole-dipole force. And this is considerably stronger than the what were we just talking about? Oh, yeah, London dispersion force. All right. So the dipole-dipole force comes from attraction between two permanent dipoles. All right. So London dispersion was all about temporary. All right. Now we're dealing with permanent dipoles. So in order to participate in this force, if you will, you have to have a permanent dipole. All right. Molecule must have permanent dipole. All right. So if we go back to bromine, for example, can bromine exhibit the dipole-dipole force? And the answer is no. All right, there's no permanent dipole. Okay, bromine and bromine, those electronegativity values cancel out. All right. What about? Let's go back to pentane. All right. Now, pentane is going to also be a compound that does not have a permanent dipole. All right. If we look here, we've got carbon bonded to carbon, carbon bonded to carbon, carbon bonded to carbon. Yeah, so we've got no permanent dipole there. You may ask, well, what about those hydrogens there, right? Remember those guys? Well, the electronegativity difference between carbon and hydrogen is so small that we can basically treat that as nonpolar, which means it does not contain a dipole. So hydrocarbon molecules like pentane are going to be nonpolar, and they are going to have zero dipole-dipole forces that we're going to consider. All right. What about the molecule? Oh, let me say, yep, urano. Okay. Let me make it a little more dramatic. All right. So bromine, no dipole-dipole forces. Pentane, no dipole-dipole forces. But recall, they do have London dispersion forces. All right. What about the molecule carbon monoxide? All right. Carbon monoxide. All right. What do you think? Well, carbon is less electronegative than oxygen. So I'm going to see something like this. All right. And yeah, I'm going to expect to see a dipole there, right? Permanent dipole. So yeah, carbon monoxide, dipole-dipole force. All right. How about carbon dioxide? Well, yeah, carbon is less electronegative, so I'm expecting to see this. But there's a catch here, all right? This is a linear molecule, all right? So the oxygen on the left is pulling with the same strength as the oxygen on the right, and they're 180 degrees apart. So it's like a tug of war, right? They're canceling each other out. So even though there is a dipole between the carbons and oxygens, the oxygens and the carbon, there's no permanent dipole. So carbon dioxide is a no, all right? Does not participate in the dipole-dipole force. But what if I changed one of those oxygens to a sulfur, this strange compound here, all right? So now I've got a delta minus on oxygen, a delta plus on carbon, and a delta minus on sulfur. All right, sulfur happens to be a little more electronegative than carbon. However, sulfur is not pulling with the same force that oxygen is, right? Oxygen is more electronegative than sulfur, so guess what? The electrons are going that way, and I can have a dipole-dipole force present in this molecule, all right? So let's take another look at the molecules and ask what's going on here. Let's look at the molecule acetone, all right? So this is a very common organic solvent. You probably used it in household chemicals and fingernail polish remover and so forth, all right? So does this molecule have a permanent dipole? And the answer is yes. all right, we have the delta minus on the oxygen and a delta plus on the carbon. So I expect to see my dipole going in that direction. All right. What about an analog where we remove the oxygen? All right. Which of these two molecules do you think is going to have a higher boiling point? All right. Back up. How do we answer that question? So higher boiling point. Okay. What does that mean again? That means which one sticks together better. It takes more heat energy to get them to break apart. All right. So higher boiling point is going to have better intermolecular forces. So who's going to have the better intermolecular forces? Let's look over here. Acetone, this guy has what? Dipole-dipole. And this guy over here to the right, does it have dipole-dipole? Nowhere near as good as the one on the left, right? I mean, you've got this oxygen, a delta minus, and a delta plus. And remember, we talked about carbon-carbon bonds being, non-polar, so I don't see anything in here that indicates that we've got a significant dipole-dipole. All right, so I would say this guy is probably just London dispersion. It's kind of where it tops out. So which one's stronger, dipole-dipole or London dispersion? The answer is dipole-dipole. All right, so we can get the book out here. The boiling point for acetone is 56 degrees Celsius. The boiling point for this hydrocarbon over here is -7 degrees Celsius. All right, significant, much, much different. All right, and that's all coming from what? The dipole-dipole force being significantly stronger than the London dispersion force. So before we move on, does acetone, this molecule on the left, does it have London dispersion forces? Yes. Every single molecular compound in the universe has London dispersion forces. All right. We move up the chain to the dipole-dipole, a little more selective. Not every molecule has dipole-dipole forces. All right. The only ones that do are ones that have permanent dipoles. All right. Okay. The next one is enormously important force called hydrogen bonding. And it's a little bit of a misnomer. We're not actually talking about covalent bonds to hydrogen, all right? But this intramolecular force of the three is the strongest, all right? So this is the strongest van der Waals force, and van der Waals is abbreviated VDW, believe it or not, all right? Okay. And this one is even more selective than the other two, all right? So what you have to have in order to participate in hydrogen bonding is we need to look at two things. We need to have something called a hydrogen bond donor, all right? And we'll talk about the acceptor in a moment. So a hydrogen bond donor is a molecular compound that contains a hydrogen atom bonded to fluorine, oxygen, nitrogen, or chlorine. All right, so I'm going to put a little asterisk by fluorine and chlorine. All right, yes, they can be considered hydrogen bond donors if you have a hydrogen bonded to fluorine or chlorine, but we are almost going to be focused on solely oxygen and nitrogen. All right, and the reason why is the list of compounds that hydrogen and fluorine share a bond is trivial. all right? If you have hydrogen bonded to a fluorine, that's it, all right? You have HF, okay? Same with hydrogen and chlorine, all right? There's probably a few more compounds out there. I can't think of any at the top of my head that you can have chlorine bonded to other things outside of just the hydrogen. But, you know, this is trivial, all right, where it's just HF and HCl. So that's not all that interesting, all right? Where things get fun is where you have hydrogen bonded to oxygen and nitrogen. So you may be asking, well, why are we just talking about these four elements, right? Fluorine, chlorine, nitrogen, and oxygen. Well, those are the four most electronegative elements on the periodic table, all right? And what happens when you have hydrogen bonded to something like oxygen, all right? And I'm not drawing the full molecular compound here. I'm just showing H bonded to an oxygen. Oxygen is massively more electronegative than hydrogen, all right? So what we would say here is you have something like boom, all right, this giant delta minus, all right? And then you have a giant delta plus that would result, all right? So this dipole is enormous, right, relative to, you know, let's say like a carbon-oxygen bond or a, you know, a bromine-chlorine bond, something like that. This HO bond is massively polarized, all right? Same with hydrogen and nitrogen, just not to the same extent, all right? Remember, oxygen has an electronegativity value of around 3.5, all right? And nitrogen has an electronegativity value of around 3, all right? So, and fluorine maxes out at 4, all right? So the nitrogen barely makes it, all right? So does chlorine. They barely make it, all right, into this, what we call hydrogen bond donor qualification, all right? But it's significant, all right? So we're going to see hydrogens bonded to oxygens and hydrogens bonded to nitrogens as being hydrogen bond donors, all right? So we'll get into what that means here in a moment. Next thing we need to talk about is something called a hydrogen bond acceptor. A hydrogen bond acceptor is a molecule with a negative dipole. All right. So if we look back at acetone, I want to ask a few questions. Is this a hydrogen bond donor? Okay. So how do you qualify as a hydrogen bond donor? Well, a hydrogen bond donor needs a hydrogen atom bonded to nitrogen or oxygen. Remember, we said fluorine and chlorine, but we're just going to kind of keep those in the back of your mind for when you take biochemistry, all right? But we're just looking at oxygen and nitrogen, okay? This molecule does contain oxygen, all right? However, oxygen does not have a bond to hydrogen. It's got a double bond to carbon, all right? So the answer is no, okay? It is not a hydrogen bond donor. All the hydrogens in that molecule are actually bound to what? Carbon, all right? So now can we talk about, all right, hydrogen bond acceptor? All right, so what do you need to be a hydrogen bond acceptor? You need a negative dipole, all right? And guess what? We've got one, all right? Oxygen's got a delta minus on it, all right? So that delta minus right there makes this guy a hydrogen bond acceptor, all right? All right, let's take a look at the molecule water. Does it have a hydrogen bond acceptor? HBA. That's not an official acronym by any means. I'm just being lazy. All right, so is it a hydrogen bond acceptor? So again, what do you need to become a hydrogen bond acceptor? You need negative dipole. Does this molecule contain a negative dipole? Yep. All right, so the answer is yes. Is it a hydrogen bond donor, HBD? What do you need to be a hydrogen bond donor? Well, you need to have a hydrogen bonded to either an oxygen or nitrogen. Ding, ding, ding. Yes, we've got that. All right. So a molecule can be both an acceptor and a donor. All right. That's totally fine. This, by the way, is what makes water such a magical little compound. All right. So you've probably heard a lot of times in science, water is an amazing molecule, and it certainly is. All right. And one reason it is amazing is its hydrogen bond donor acceptor capabilities. All right, so let's look at two water molecules. That would be, let's say, in the liquid phase. All right, so here we've got our delta minus and our delta plus. Here we have our delta minus and a delta plus and a delta plus. Oh, and I forgot a delta plus over here. So what ends up happening here is we get a attraction. All right? And this attraction happens to be a hydrogen bond donor acceptor attraction. So what we have in blue there is something called the hydrogen bond. Now, like I said, it's a bit misleading, all right? And I didn't come up with a name, but it is not a covalent bond to hydrogen, all right? The covalent bond for hydrogen, I'll put in yellow here, is right there, all right? In blue, that is the hydrogen bond, which is the van der Waals interaction or the attraction between hydrogen and another oxygen in a separate molecule, all right? So this is, again, an intermolecular force, all right, between two molecules. But what's cool about this is I can put another water molecule over here, and I can put another one over here, one over here. You can imagine what's going on in a glass of water, right? All these water molecules are attracted to each other through hydrogen bonding, which again is the strongest of the intermolecular forces, all right? So water is amazing because every single atom in its structure is participating in hydrogen bonding somehow. So it's got three little atoms, and all three of those dudes are hanging out doing hydrogen bond accepting and donation. There's no other molecule that does that, all right, as effectively as water does, all right? So let's just take a look at what that does to boiling point, all right? So let's go back to acetone versus water. Okay, and let's go through some questions here. Does it have London dispersion forces? Answer is yes. Does it have dipole-dipole? Answer is yes. Hydrogen bond acceptor, hydrogen bond donor. It is an acceptor, but it is not a donor. All right? Water, we're going to go through the same ones. I'm just going to change my colors to blue. Dispersion, yes. Dipole-dipole, yes. Hydrogen bond acceptor, yes. Hydrogen bond donor, yes. All right? That hydrogen bond donor makes a big deal. All right? Once you hit hydrogen bond donor, you have very strong intermolecular forces. All right? So what happens in the case of acetone, I think we said 53 degrees C, thereabouts. It's not a big deal. Boiling point of water, something you should have committed to memory is the boiling point of water on the Celsius scale, 100 degrees. It's almost twice the boiling point of acetone. And look, acetone's got carbon, 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 oxygen, 4 heavy atoms, right? And you think for dispersion reasons it should dominate. on water, because water only has the one heavy atom of oxygen. But that hydrogen bond donation force, man, that's just kicking it into high gear, and we've got a very high boiling point for such a little molecule. All right? So it can even be more dramatic. Let's take a look at water, all right, versus a sulfur analog called hydrogen sulfide. All right? So again, if we look at group 16 on the periodic table, oxygen is at the top, sulfur, selenium, and, oh goodness, what's below that? Telluride, tellurium. All right. So what are we looking at here? Okay. Just going through the intermolecular forces, dispersion, all right, they both have it, but hydrogen sulfide should beat it on dispersion. All right, sulfur is a larger atom. But where's water going to beat it? All right? Well, they both got dipole-dipole, but water's going to have a stronger dipole, right, because of oxygen being more electronegative. But where the real kicker is this guy can hydrogen bond donate. All right? It's a hydrogen bond donor. This guy cannot be a hydrogen bond donor. All right? So the hydrogen bond donor, nope. All right? So the fact that this guy can hydrogen bond donor, it should have a higher boiling point. All right? And let's see if we can't quantify that. Of course, we know this to be 100 degrees C. Get a load of this. Minus 60. All right? So we're talking 140 degrees difference in boiling point. That's bananas. All right? And the molecules are almost identical, save for one thing. You swap oxygen out for sulfur, you would think, oh man, yeah, this should go better for H2S because it's a larger atom, better dispersion. Nope. Hydrogen bond donation is just, man, dominant. All right. So hydrogen bond donors, big, big deal. All right. So let's look at nitrogen-containing compounds. All right. The molecule ammonia. Okay. You say like, oh, that's kind of like a water analog. Yeah, but not really. All right. What's happening here is we've got hydrogen bond donation. All right. Let's draw water over here for comparison. They're both hydrogen bond donors. But ammonia, the molecule on the left, NH3, all right, you say, oh, wow, you got 3 hydrogens, all right, so it should have a higher boiling point than water, right, because water's like, yeah, I only got 2 of these hydrogens to hydrogen bond donate with. Answer is no, all right, ammonia is a gas at room temperature. Why is that? Okay, 2 reasons. Nitrogen is not as electronegative as oxygen. So that electronegativity difference gives us a smaller delta plus. Okay? And that smaller delta plus, what that's going to do is it's going to reduce the hydrogen bond donation capability of ammonia. All right? So when the hydrogen bond donation capability of ammonia goes down, all right, it doesn't stick together as well. All right, so water is going to dominate. All right, on boiling point here. So little lesson here: oxygen, more electronegative than oxygen. It's a better hydrogen bond donor than nitrogen is. All right, nitrogen's not bad, but oxygen is much, much better. And just to give you an idea here, the boiling point of ammonia is negative 33 degrees C. So as I said, at room temperature, which is 25 degrees C, this guy would be completely vaporized. All right. And the boiling point of water is, of course, 100 degrees C. All right. So even though nitrogen can hydrogen bond donate, all right, we can see it's nowhere near as good as water is. All right. Okay. One final question on this. All right. Which one of these is going to have the highest boiling point? All right. We've got H2O, which is, of course, water, H2S, hydrogen sulfide, and H2SE, hydrogen selenide. All right, and these guys all come from group 16. So again, to recap, we go oxygen, sulfur, selenium, tellurium. All right. So, highest boiling point. Which one has the strongest attractive forces? It's going to be water. All right. Water has the highest attractive force. Why? Well, these molecules are all similar, right, in build. And what I mean by that is two hydrogens and one heavy atom, two hydrogens, one heavy atom, two hydrogens, one heavy atom. All right, so they're built very similarly. They all have a central atom from the same group. So typically what you do is you'd be like, all right, well, whichever one's the biggest is going to have the highest boiling point, like we did way back with chlorine and iodine. No, this one's going to be the highest boiling point because of what? That hydrogen bond donating quality, all right? It has HBD, all right? So it's going to be H2O. Okay, what about second highest? It's tempting, isn't it, to go for H2S. Why? Well, we like periodic trends. We like to just go straight down columns or cross rows, whatever. But something happened between H2O and H2S, right? The difference was what? That hydrogen bond donating capability, all right? Once you get down into H2S versus H2SE, hydrogen bond is off the table, all right? Then it comes down to either dipole-dipole forces or dispersion forces. And it turns out dispersion forces are going to dominate here, and H2SE is going to have the second highest boiling point. And then the lowest of the three, well, process of elimination, it's H2S. All right? So of those three, that's the series. All right, let's try another series of compounds. Let's try chlorine, bromine, and iodine. And this is actually a review. Highest boiling point. These guys are in group 17. We got F, Cl, Br, and I. Okay. Well, there's hydrogen bonding is out of the question. Well, what about the chlorine? Remember, it has to be what? Hydrogen bound to it, right? So we don't have that. Okay. So it's just chlorine bonded to chlorine, bromine bonded to bromine, iodine bonded to iodine. And there's no dipole-dipole forces. It's dispersion only. So it's going to be I2, all right? And then the lowest boiling point can be Cl2. It's the smallest, all right? So you need to be able to be fluent with these three forces all interacting at the same time, all right? So I'm going to kind of wrap up here with a biochemical example here. If we look at DNA base pairing, all right, so you remember from your old biology classes that you got AT, CG, or whatever that was, right? Well, what it turns out to be, AT is adenine, thymine. All right, so the DNA strand is a double helix, all right, and it's held together by these base pairs, all right? The adenine thymine is one, and the other one is cytosine guanine. But we're just going to look at the AT for an example. The GC works the same way. But how are these base pairings, what are they talking about there? All right, so what I'm going to do is draw these compounds, all right? So remember we were doing line angle structures earlier, all right? So that is a six-membered ring structure there, all right? So each one of these intersections on the ring would be considered to be a carbon atom unless you write in something like N, all right? That means there's a nitrogen atom part there, all right? So I'm not holding you responsible for being able to completely translate these structures. And right there tells me I've got a double bond between nitrogen and carbon. And I've got nitrogen there with 2 hydrogens on it. All right, so don't get confused by all the symbols on here, all right? Just go with what you know, all right? What do you see on this molecule that just really stands out to what we've had in our discussion today? Right here, that NH bond, right? Why is that important? That NH bond tells me that I've got what? A hydrogen bond donor, okay? So this guy right here is going to be a donor. Okay. Anything else important on this molecule? Well, these nitrogens are more electronegative than the carbons they're bonded to, so they could technically be acceptors. All right. Oh, pardon me, the molecule I've drawn here, this is adenine. All right. I'm going to draw a thymine next to it in green. All right. Isn't this neat right here? Parked right next to where the donor hangs out is an acceptor. Okay. How did I know that would be an acceptor? That atom right there that I'm drawing the red on, that's what atom? Intersection of 2 lines, that's a carbon atom, right? Carbon attached to oxygen, that's a delta minus, okay? So I've got the donor and the acceptor. Boom. I've got a intermolecular hydrogen bond, okay? Look here as well. Hydrogen bond linkage there. So what ends up happening is the structures of adenine and thymine are just right to where they can lock together in this hydrogen bond donor acceptor base pairing, and it allows them to link up, all right? Guanine would not link to thymine like this because they are not organized in the same way. So it's almost like a lock and key, if you will, all right? However, guanine and cytosine, they fit together just right. And the way this works is if you have the right base pairing, then they will lock together, build this beautiful dihelical structure, and life exists as we know it, all right, from DNA. So this little hydrogen bond thing that, I've kind of been real excited about talking to you about today is big deal in biochemistry and organic chemistry. And as you can see, life as we know it, water exists in liquid form on this planet, which is quite important due to hydrogen bonding. So every time you see a glass of water, think about those little donor-acceptor pairs, all right? Okay, well, that will conclude our video lecture for today, all right? I'll be posting 2 more on Tuesday, so take care, everyone.